Welcome to the third lecture by Codeverse for the quantum computing workshop. Today's topic will be quantum algorithms. Before I start talking about algorithms, I'll like to brief upon a few topics which I think are essential to understanding the algorithms themselves. The first one is the wave mechanical model of an electron, which is the basis really of quantization of electron energy. So you can think of electrons as both particles and waves because a property associated with quantum particles is the wave particle duality. This means that quantum particles can exhibit both particle like and wave like behavior at the same time. So the energy associated with an electron in its wave form is given by h times nu, where nu is the frequency and h is the Planck's constant, which is 6.626 times 10 raised to minus 34 kg meter square per second. So quantization of energy is really just linked to quantization of frequency. And there are only a few discrete frequencies which are possible for an electron to have. For instance, if you have a frequency which could cause destructive interference when the wave of the electron superimposes on itself, so it is no doubt that electrons interfere with each other and even themselves. That's what the Young's double slit experiment was all about. So if this interference causes destructive interference, it would really just destroy the electron, which is something that's very unstable and it's not what's preferred by nature. So it always tends towards a more energy stable state that's either by causing constructive interference or at least maintaining that wave. And this is possible by having only certain frequencies. And this is really just the backbone of quantization of electron energy. So next one we have interference, which means the superimposition or the vector sum of two waves. So if you have two waves of two quantum particles, they could influence each other and interact with each other so that they could influence the probability of the each one being found in a definite state with respect to position and time. Oftentimes, constructive interference is used in quantum computers to locate that one bit string which could be the best possible solution, so that the probability of it being the final solution becomes close to one, and it causes destructive interference on all other bit strings which could never be the solution. So the probability of finding those reduces to zero. So the first algorithm we have is the Grover's algorithm, and it's used to search for values in an unsorted database. So the first step associated with it is to apply a Hadamard gate. And now a Hadamard gate creates a superposition of all possible states of a qubit. So it just really creates an equal probability of each state being found, unless it's unmeasured. So when it's measured, it would reduce to one discrete possibility. And then we apply the Grover diffusion operator, which is the heart and soul of this algorithm, really. And then we measure the resulting quantum state. So geometrically, you can think of Grover's algorithm as an initial vector, which is called the state vector, and which you can see right here. This is the state vector, this ket S, and ket omega, I believe, is the target vector. So you perform a series of rotations using transformations and matrices such that the state vector gets rotated towards the target vector. And this is done by using the Grover's diffusion operator. And the first step is always to create a superposition. So that's by using a Hadamard gate. And this is the general form of superposition created by a Hadamard gate. So over here, n is the total number of combinations that the qubit can have or the bit string can have. So if you have a bit string with n number of qubits, you essentially have 2 raised to n possible combinations. Okay. Then we have the oracle operator. And what this does is it flips the sign of a bit string or a qubit if that happens to be a solution, if it happens to be, a good enough solution at least. So it will flip the sign by using interference again. So it will really just, change its phase. That's all I can say. And if it doesn't match with the answer, and if it, seems contradictory even, there wouldn't be any operation done on the bit string. So it will be left as it is. And then we use interference such that we can amplify the probability of the correct answer being found. Now, the correct answer will be the one which we flipped the sign of, which we reversed really. And we need to perform this rotation k number of times. And k is given by pi over 4 times root n, where n is the total number of possible bit strings. So that will be 2 raised to the number of qubits in each bit string. And the state of the vector, not just before rotation or at the final state, at any point of time really, it's given by sine of 2k plus 1 times theta times ket omega, which is the final target vector, plus cos of 2k plus 1 times theta times ket orthogonal. And over here, orthogonal is just another vector which is perpendicular to the target vector. So it would be this ket s dash, which you can see right here. Okay. And you can just see that this vector is in the form of the orthogonal vector and the final state vector. So it's really just a combination of these two components. It's a linear combination, I would say. And that's how a vector is expressed. So if you have I hat and j hat, you have 3 I hat plus 4 j hat, which you may remember from physics. This is just another form of expressing it, but our I hat and j hat have transformed into another vector, which is the targeted vector and the orthogonal vector to it. And the angle between the solution state, which is the targeted vector, and the initial state is given by sine inverse of 1 over root n. And the probability of some answer being the correct answer is given by sine square of 2k plus 1 times theta. So as we approach pi over 4 times root n, as k approaches that number, we are essentially just getting closer towards the final answer. So hence at k equals pi by 4 times root n, this value would be equal to approximately 1. It would be very close to 1, but not always 1. That's a major drawback quantum computers have, is that all calculations are probabilistic, and you can never be 100% certain of the answer. That's a quantum trade-off, I would say. So this is a simple demonstration of this algorithm using an array or a list. So imagine you have this state, that's psi, given as like 4 halves. And you have this third element as your actual answer. So we would reverse its sign, we would apply a minus half to it. And because that would be our correct answer, we need to make sure that the probability of finding that answer is 1. So the first step to achieve this is to find the average of all values we have. So it would be 3 times half minus half over 4. So that would be 1 over 4. And then we do the inversion around the mean of a number, which is basically the operators and the projections that we used in the actual algorithm. So what we do right here is we take each number and we reverse its sign and add the twice of the average. So if you look at look over here, we reverse the sign of half and we add twice 1 over 4. So it would be minus half plus half, which is 0. So the probability of finding this as the final answer reduces to 0, which is good because we don't want any wrong answers in our output. However, if you look at minus half, which we intended to be our actual answer, the probability of finding that would be minus of minus half, that's half, plus twice the average, which is 1. So that's great news for us because the probability of finding the correct answer is 1, and the probability of finding the wrong answer reduces to 0. So this is a very simple explanation of the algorithm. This isn't what quite happens on the quantum scale. It's often involving complex numbers and interference, which can be too complex for the course of this lecture. So to conclude, it is because of such superposition and interference really that quantum computers are more efficient than classical computers. So as I mentioned earlier, we need pi over 4 times root n steps. So that's even less than root n steps that we require for this algorithm to complete properly. But for a classical computer, however, we would require n steps. So a quantum computer can really just analyze the entire data set, which is often very large. It can analyze that in a lesser number of steps, so that would be more efficient. So next we have the Bernstein-Vazirani algorithm. And before talking about that, I would like to introduce you to a few states, which are denoted by ket0, ket1, ket plus, and ket minus. So you can imagine ket0 and ket1 as unit vectors. So it would be synonymous with I hat and j hat, if you remember. So from this diagram, I would consider this red arrow, this red vector, to be ket0, which is really just I hat. And this would be ket1, which is j hat. And ket plus is a superposition state. So it would be a linear combination of ket1 and ket0. So it would really just be another vector in between those two vectors. And if we consider ket minus, we want the probability of finding ket0 and ket1 from ket plus and ket minus to be the same. But the only difference here is the angle between them. So if I had to draw it, yeah. So because ket minus includes this minus ket1 that you see right here, we need to ensure that the direction of ket1 is also reversed. So we have ket1 in the opposite direction, which is minus y-axis. So we can have any other vector in between them. It could be something like this. So we can really just express the superposition of both vectors in terms of ket0 and ket1, but the only difference between them is the angle. So in quantum terms, we can call this as the phase. Next up, we have the Bernstein-Vazirani algorithm, and it's used to identify a bit string. So before moving on to the quantum version, I would like to talk about the classical computer version. So when you consider a classical computer and you give it any number, let's say you give it 9. Now the binary equivalent of decimal 9 is equal to 1001. Now how this would really analyze and deduce that the number you have given is 9 is by comparing and using AND operations for each bit in the bit string. So this would be 1 bit, so this 1 would be 1 bit, and this 0 would be another bit, and this entire bit thing is called a bit string. So how it would go about this is it will have a number of zeros followed by a 1. It would then compare if both values are 1, and that's by using an AND operator. And if it is, it would deduce that the bit at this place is also a 1. And if it's not, it could conclude that it's a 0. So it just goes about and performs n iterations and finds the final bit string in that way. For a quantum computer, the algorithm looks a little different. So you have the initial bit string, that's 1001, let's just consider that. And we have 4 qubits. Let's have the 4 qubits as Q1, Q2, Q3, and Q4. And we initialize those to the 4 bits that we initially have. And then we entangle those qubits to the two classical bits. And those classical bits, let's keep it as C0 to C3. We add another qubit, which is Q0, and this qubit is essential for our quantum circuit to work. So the first step involved in our circuit would be to apply Hadamard gates to the first 4 qubits, and this puts them in a state of superposition that's denoted by Ket plus. Now for the last qubit, we apply a poly X gate, which is a NOT gate. So this reverses the sign, and then we apply a Hadamard gate. So this will really just create a superposition again, but it would be denoted by Ket minus. Then we apply a C0 gate on all the qubits, and a C0 gate is the quantum version of the AND gate. And what it does really is if the control gate just applies the poly X gate. So if you have the target vector, over here the target vector would be Q0 and Q3. So it's these dots that you see right here. And our control qubit would be Q4. So it is the plus that you see. So it just applies a poly X gate, which means it reverses the sign of the qubit on the control qubit. So over here, if the on the target qubit, I apologize, on the target qubit, it reverses the sign if the control qubit is in state 1. So if this is in state 1, the signs of these 2 qubits will be reversed. So that's what it does really, and it acts as an AND gate for quantum computers. Now, because Q4 has X, which is NOT gate, a Hadamard gate, and a C0 gate, it undergoes something called phase kickback. And this results in an extra minus sign. And you can imagine the reason for phase kickback really to be quantum interference. So it is this beautiful interference that takes place and efficiently reverses the sign when needed. And this extra minus sign gets put back into the control bit. That would be Q0 over here. Then we have another extra minus sign, which gets put back into the third qubit, which is Q3. And then we apply a Hadamard gate to the first 4 qubits, and we record those or measure those superposition states. And then we link those superposition states with the classical bit. So if the superposition comes out to be Ket minus, we know that the classical bit is 1. And if it is Ket plus, we can have the classical bit as 0. So it is just this way that we can analyze what a bit string is by using quantum circuits. And one important point to note right here is that these processes happen simultaneously because all qubits really just exhibit superposition. So you have all possible states at once. So it just takes one step, which is much more efficient than the n steps required for classical computers. So even though this algorithm isn't quite practical, it's very useful to show how quantum computers are much efficient. So this is a circuit which I developed in a quantum circuit simulator that's called the Quantum LAN, which I'll be showing towards the end of the presentation as well. The next and the last one is the Deutsch-Jozsa algorithm, and it's used to determine constant or balanced functions. So constant functions mean that the function value is all zeros or all ones for all x's. But balanced functions mean that the value of the function is 0 for half inputs and 1 for the other half the inputs. Okay. And once again, this takes only one step to solve as compared to 2 raised to n steps for a classical computer. So our first assumption or our initial state of the system is n zeros, which means ket 0 tensored with itself n times. So it will really just be a bit string of 0, 0, 0 n times. And the superposition state would be ket minus. Then we apply a Hadamard gate to this initial state. And this would just create another superposition of all possible bit strings. So as you can see over here, this Hadamard gate tensored with itself 3 times, which means that we add all the possible bit strings of length 3 in such a way that the probability of finding each is equal. So as you can see from here, the general expression for the Hadamard gate becomes the following. So it's 1 by 2 under root of 2 raised to n, where n is the total number of bits, times the summation of the total number of possible bit strings. Okay. Then we apply a unitary oracle called UF, and this is basically our function. So it's again the soul of this algorithm. So we apply this function to each and every qubit individually because we are unsure of what superposition each qubit is in. So we have to apply individually. And then we omit ket minus because it's not relevant, and we apply another Hadamard gate. But before we do that, we need to find what the Hadamard gate would be like and find its general expression. So now that we have the unitary oracle, this introduces something called the phase factor, which is really just a manifestation of quantum interference. So if you have the Hadamard gate of ket 0, you have the final state as 1 over root 2 of ket 0 plus ket 1. But the Hadamard gate of ket 1 would be 1 over root 2 ket 0 minus ket 1. Now, if you analyze this for H tensor with itself 3 times, you can get this expression. So this may look very complicated, I acknowledge that. But if you look at it closely, I'll just zoom in. Yeah. If you look at it closely, you can see that the coefficient or the power of -1. So -1 is basically the phase factor which I was talking about. Now the power of -1 is directly linked to the position of 1 in the bit string. And that's because we mentioned earlier that the Hadamard gate, when applied to ket 1, would result in minus like ket 1 in the final state. So it is really just a consequence of that. So you have the phase factor directly dependent on the position of 1 in the bit string. So you when you group these powers together, it becomes much more apparent. You can infer that the sum of the positions or the indexes of each bit string is correlated to the position of 1 in that bit string. So you can basically just express it as a dot product of the bit string itself. And that is why our final expression becomes this. And as you can see here, it's -1 raised to x dot z, where z is the final bit string. Okay. Now I will perform a simplification of the circuit or of the algorithm. So for constant functions, as I mentioned earlier, it's either all zeros or all ones. So that's one point to keep in mind. Okay. So we have applied the Hadamard gate over here, and we have found an expression for it, which is what I just showed in the last slide. So we can take this 1 over root 2 by 1 by root of 2 raised to n and multiply it with this coefficient over here. So we get 1 by 2 raised to n. And this will become the summation of all bit strings belonging to a bit string of a given length of this term right here. But our initial state was assigned to be n0. So it's 0 tensor with itself n times. So this dot product right here, it would really just be x dot 0, 0 n times. So this would reduce to 0, and we just have the final relation as -1 raised to f of x. And then we simplify that for either all f of x equal to 0 or all f of x equal to 1. So if every value of the function is equal to 0, we have -1 raised to 0 for all values in the function, and -1 raised to 0 is 1. So we add 1 with itself as many times as there are combinations of n of a bit string with n bits. So the number of combinations that a bit string of n bits can have is 2 raised to n. So we add it with itself 2 raised to n times. So if the value of the function is 0, it would be 1 by 2 raised to n times 2 raised to n. And if the value of the function is always 1, it would be 1 by 2 raised to n times minus 2 raised to n. Okay. So this means that if the function is constant, we have the final output as always plus or -1. But if the function is balanced, we have an equal number of +1 and -1. So if we add those, we eventually get the output as 0. So to conclude, if the function is constant, we have the output as plus or -1, and if it's balanced, it's always 0. Now, a final question I would like to talk about is why 1 by root 2 is present as a coefficient for the output of the Hadamard gate. So an important point to consider is the fact that Hadamard gate and the matrix itself is symmetric and it's unitary. So this means that when we apply a Hadamard gate to a qubit or some superposition state, we need to get that state once again. So this really just means that the Hadamard gate is its own inverse transformation. So that marks the end of my presentation. I will be sharing my screen once again to demonstrate the circuit. Just give me a moment. Right, so this is the circuit for the Bernstein-Vazirani algorithm. And as you can see here, the output is 1001, which I hope my screen is visible. Can someone please confirm?
Yeah, it's visible.
Okay, great. So the final output would be 1001, which is 9 in decimal. So now you may wonder why is the output 1001 when the bit string could really just be anything. So that's because of interference once again. So based on how the qubits form our actual bit string, the interference pattern happens in that way, and the control bit and the C0 gate just operates in that way and has its target qubits such that the final output would be equal to the initial input. So let's say I had to change this control bit to Q1. So it would be 1. This would change my output to 1010 as opposed to 1001 initially. Another point I would like to highlight about Hadamard gates is as I'm demonstrating here, I've applied Hadamard gates to all 4 qubits. So I'm essentially putting all qubits in a state of superposition. So this is the probability of finding the qubit in that given state. Of course, this is just a simulation, so it can be really value any, really. And if you consider here, the values are different. So it just means that the probability changes and you can just find a qubit in any given value. And I'll apply a Hadamard gate once more. So if we apply a Hadamard gate to itself, twice, we should be getting the initial state. And the initial state is 0. So this just proves once again that the Hadamard gate is its own inverse transformation and it's completely symmetric. So yes, that's the end of my presentation. I'm more than happy to welcome any answers, any questions, sorry. Right, so I have a question. How would the addition of an additional phase shift in the Grover diffusion operator affect the angle theta? Okay, so again, this depends because you see the operators, they perform that function based on what seems to be the correct answer. So it reverses the sign only if something happens to be correct. So the addition of an additional phase shift, this would most likely reduce the number of iterations or increase. So it would be really difficult to analyze what the actual number of iterations would be because based on the calculations we have right now, it would be pi over 4 times root n. But now that the phase angle is shifted, that number needs to be different so that we don't deviate from the targeted vector. But there needs to be more calculation done about it, I believe. I hope that answers your question.